All right, let's dive right into this explainer. If you've ever spent weeks or honestly sometimes months slogging through a massive framework migration or a sprawling Java version upgrade, you know exactly how painful it can be. It's a grind, right? Well, today we're looking at a fundamentally different approach to conquering that overwhelming mountain of technical debt. We're talking about OpenRewrite, and it represents a huge shift from tedious manual labor to precise, deterministic automation.
Now, here's the core dilemma we're facing when we look at all these shiny new automated refactoring tools. Would you trust a tool that fixes 90% of your code but quietly breaks the remaining 10%? We all want that magic button that just fixes everything, right? But when you're dealing with an enterprise code base that has millions of lines of code, a 90% success rate isn't a victory, it's a massive liability. If an automated tool quietly breaks even a fraction of your code, the time you spend tracking down those incredibly subtle bugs is going to completely erase any time you saved in the first place. That's the exact problem we need to solve here.
So let's start with Section 1, the tech debt crisis and the crushing burden of legacy code.
Think about how many hours your team loses just updating dependencies, changing package names, or making that huge leap from Java 8 to Java 17. Millions of hours are literally lost to framework migrations and manual dependency updates across the industry. It ties up engineering teams for weeks doing repetitive, low-value labor. It's not the kind of work that drives product innovation, is it? It's just keeping the lights on. And frankly, it's exactly the kind of work that we humans are just bad at. We get bored, we miss things, and we inevitably make mistakes.
And the pain points of manual migration are everywhere. Imagine a scenario where you're migrating a core library on a feature branch, but other teams are out there simultaneously adding new features on the main branch. By the time you're ready to merge, your branch is hopelessly out of date. You've got error-prone merges, massive coordination overhead, and you almost always miss those weird edge cases. It is basically a recipe for merge conflicts and developer frustration. Which brings us to Section 2, deterministic versus probabilistic AI. Or basically, the hype versus the reality in refactoring.
This is a classic black box versus clear box situation. On one side, you have probabilistic AI, like your typical large language models. They guess what you mean and focus on giving you a complete answer, even if that means risking subtle bugs or hallucinating code. They operate on probability. But deterministic automation, which is what OpenRewrite uses, focuses squarely on correctness. It's driven by structured, lossless semantic trees. It ensures the code remains fully compilable, and it guarantees that a specific input will always, without fail, yield a specific, safe output.
Because, listen, you simply cannot afford to let probabilistic models guess their way through a massive enterprise migration. The cost of false positives is just astronomical. Now, don't get me wrong, AI coding assistants are absolutely amazing for generating a new function or suggesting a quick snippet, but asking them to refactor an entire monolithic application, that's dangerous. They don't have full semantic awareness. They might change a method signature that completely breaks a downstream dependency they didn't even know existed.
So, how do we fix that? Let's look at Section 3, the do no harm principle, and prioritizing correctness over completeness.
There's a quote from the source material that really hits the nail on the head. It says, "We must prioritize deterministic correctness over attempting to guess what the user intended." This exact philosophy is what separates OpenRewrite from AI-assisted code generation. It's actually better to leave some code entirely untouched than to incorrectly modify it. OpenRewrite won't guess. If it doesn't have 100% confidence that a change is safe, it just won't make the change. Under this do no harm principle, correctness will always win.
And just to be super clear on what we mean by deterministic, it's a system where the exact same inputs will consistently produce the exact same outputs, zero probabilistic guessing involved. By focusing entirely on these strict rules, OpenRewrite will never apply a transformation unless it is mathematically certain that the change is syntactically and semantically safe. When you run a recipe, you know exactly what's going to happen. It's reproducible, it's verifiable, and most importantly, it's safe. That determinism is the secret sauce that lets you scale these transformations across thousands of repos without losing sleep.
Let's crack open the hood in Section 4, Lossless Semantic Trees Explained, the Clear Box Approach.
Now, standard compilers use what's called an abstract syntax tree, or AST. That's great for a compiler because it strips away all the formatting and comments to create a lightweight binary. But if you try to rewrite code from an AST, you completely destroy the original developer's style. Git diffs become a nightmare. Instead, OpenRewrite builds a lossless semantic tree, or LST. The LST preserves everything. It keeps those non-semantic elements, it adds global type attribution, and it results in super clean, readable Git diffs that actually blend in.
A huge part of this is deep type attribution. This enriches the semantic tree with global compiler-resolved type signatures to prevent collision errors. This is huge because it allows the engine to easily tell the difference between java.util.list and java.awt.list across thousands of files. Regular expressions absolutely can't do this. A regex just sees the word list. But because the LST is type attributed, OpenRewrite knows exactly which class is being referenced, even if that dependency is buried deep transitively. It entirely eliminates the risk of false positive refactoring errors.
And then there's format preservation. Because LSTs remember the exact whitespace and comments, your refactored code will perfectly match whatever strange indentation someone wrote back in, say, 2004. You really don't want a vital security patch to result in a 5,000-line pull request where 4,990 of those lines are just whitespace changes, right? The LST ensures that if you change a variable name, literally only that variable name changes. The surrounding formatting stays exactly the way you left it. It keeps legacy quirks intact.
Okay, Section 5, Safe Refactoring at Scale. Let's look at the actual mechanics of recipes.
So OpenRewrite uses these programs called recipes that execute in a very strict phased approach. Step 1, it parses your source code into that rich LST we just talked about. Step 2, it applies a specific, targeted, type-aware recipe, like upgrading a dependency. And Step 3, it prints the code back out, keeping all your unmodified formatting completely intact. It's a brilliantly simple yet powerful loop.
But we also need to be clear about what OpenRewrite absolutely does not do. It's important to debunk the myth that it's running unsafe code. It does not use reflection, it does not execute your application code, and it definitely does not run vulnerable old libraries. Sometimes a recipe needs to look at a vulnerable library just to understand what it's migrating away from, sure, but it merely extracts the type signatures. It operates entirely statically on the LST, which keeps things completely safe from a security perspective.
And these recipes are composable. Out of the box, you get over 3,000 building block recipes that you can combine for massive framework upgrades. You don't have to write these from scratch. You can literally take a recipe for updating JUnit, smash it together with a recipe for migrating to Jakarta EE, and suddenly you've reduced weeks of toil down to minutes. It handles massive leaps, like jumping from Java 8 all the way up to Java 25.
Now, even though you can do a massive jump in one go, the recommended phased migration strategy is to avoid boiling the ocean all at once. Run these hierarchical recipes incrementally. Step 1, run the Java 8 to 11 upgrade. Step 2, review and commit that verified code. Step 3, run the 11 to 17 upgrade. Step 4, commit. It keeps your pull requests completely manageable and ensures you maintain a rock-solid audit trail.
You can even integrate this whole process directly into your CI/CD pipelines as a non-invasive dry run. This is a real game changer for tech debt. Instead of letting bad patterns creep back into the codebase, you set the CI pipeline to fail if an OpenRewrite recipe detects unapplied style changes or deprecated APIs. It basically forces the developer to run the recipe locally before their pull requests can ever be merged. Brilliant, right?
So, what are the ideal use cases here? Well, if you're just doing single-file edits, honestly, just use your IDE. But for large-scale Java version upgrades, massive framework migrations, applying org-wide code standards, or updating build configurations, this deterministic approach is the only way to do it efficiently. It's for those repetitive migrations where consistency and a clear audit trail are absolutely mandatory.
Which leaves us with a critical question. As you face down your next massive tech debt hurdle, will your next framework migration be a probabilistic roll of the dice or a deterministic guarantee? AI is an incredible tool for so many things, but when it comes to the structural integrity of your core enterprise systems, correctness has to win over completeness. By leveraging the lossless semantic tree and the do-no-harm principle, you can stop finding technical debt manually and start automating with absolute confidence. Thanks for joining me on this explainer, and I hope you're leaving with a fresh, powerful perspective on how to tackle your codebase. Catch you next time.